My name is Timothy, and I'm a principal in Fourier Image Lab, California. Today, I would like to share with you some information about the lab and also some new thoughts on image quality for automotive. And also later, in the end, I will slightly see how the tuning can improve those image quality metrics and how it links to perception. So the position of the lab in the infrastructure of vision architecture is displayed here as a sort of frequency equalizer between the ISP core provider, module house, and sensor house. So you can see this in big blocks, and those lines indicate some resistance, causing some misunderstanding or frequency mismatch between the two or three players in this system. So the mission of Fourier Image Lab is to take the requirements. By the way, these are the companies which we work currently or supported previously. And we take some requirements and translate the perception requirements into the hardware specs, sensor optimization parameters, or ISP tuning for camera. And the key services are tuning and benchmarking. So it's a loop which produces the whole value and never ends. So this is a camera life cycle loop. From new camera to new sensor, we go through tuning on initial camera, tuning on some kind of specs which are customer trying to achieve. Sometimes we change lens, and sometimes we change sensor or ISP, basically making new camera. And whenever the customer is satisfied with the specs, we are both happy. So there are three tuning targets. One target for object detection, cars, pedestrians, objects. The second is traffic light tuning model. Very different model. The traffic light model is static and the object detection model is dynamic. So hybrid model is kind of dynamic with some limitations. So depending on whether we want to see and what kind of traffic lights, we choose different parameters for exposure and other algorithms in the camera control. So key quality metrics, KPIs, so to say, which I would like to touch today are detail reproduction, dynamic range, and color reproduction. So detail reproduction is just a term which describes how far you can detect a certain object and what are the smallest detail in the image or in the captured scene which you can differentiate with some certain level of confidence. So this is an experiment we did at Pony, and you can see at different distances the same object is taken, and you can see how differently it represents at the same scale. And detail reproduction is key performance metrics for the object detection. And dynamic range and also lens flare and SNR are also linked with detail reproduction, but are slightly on different orthogonal axes, and those metrics are critical when evaluating the performance of traffic light and LED signal indicator detection. And when I think about detail reproduction, this is what the picture I kind of imagine. So it's different objects at different distances, and the more resolution you have, the better the detail reproduction is, and more details we are able to see in the object. And there are four key methods which are used in determining the detail reproduction. The first and one of the oldest one is called wedges. It's using so-called parallel lines which are coming closer and closer and those lines are at some point becoming undefinable, and we observe which level of detail we can differentiate the lines and call it how many lines we can see. The other is MTF. I will touch it a little bit deeply, and now the ISO standard is using slanted edge to determine the MTF, and it's fully automatic. It doesn't require any kind of human intention and human intervention. The more advanced method is vision chart, which I will also use describe in this presentation, and it's very critical to determine intelligence of the camera system. And newly developed direction in MTF from natural scenes, which was presented in AI conference, and the paper which describes a very interesting of MTF from natural scenes, and this could be a good supplement to the autonomous vehicles to detect some camera which is not functioning properly. You cannot rely on this method because it's scene dependent, but it can be a very good filter to look at some malfunctioning camera issues. So the first method in detail, I already described it, and you can see sometimes it's a little bit subjective to decide, but ImaTest is pretty good to find some automated threshold to find the detailed reproduction from the wedges. And the problem with it is that ISPs in modern cameras are so smart that they can reproduce those edges at different angles, and this kind of wedges not always translate into real life when detecting different objects. So the other metrics which is often used is called MTF, and the best idea to describe MTF is observing this kind of sine function with a increasing frequency, like sine of x squared or x in the power of 3. And when we capture such wave with our camera, the image which we observe is this. So as frequency increases, the amplitude reduces, and the function which shows how the frequency reduces how the amplitude reduces with the increase of the frequency is called spatial frequency response, and we plot it here and call MTF at a different frequency, like MTF 50, 20, and this is a very good objective measure of the information capacity. So ImaTest has a great tool to display MTF 50 or 20 or whichever across the whole field of view. And when we are optimizing the camera system for the field, we are trying to find minimum of deviation of this MTF across the field of view to keep the object in range. The other, what I'm not touching here in this presentation is how to measure the MTF at different distance, so-called depth of field, and maybe I'll post it in my blog a few weeks later. And here is next metrics which is used for the detail reproduction, which is called vision score from vision charts. And here we observe vision chart, take a picture of it with different cameras, and observe which line we can read with confidence. So you can see here is an image which kind of objectively has lower sharpness and lower MTF than these two images, but information capacity of this image is higher. So it's because we can read a lower number. So it's important to understand and separate the metrics and real information capacity of the camera. At Pony, when I was working here, our vision score metrics of our cameras, which we had, and this is iPhone 12, which was a reference at that time. So you can see good reference point for vision capacity. 10 means that the chart was captured from 10 feet, and 8 means how many lines we can see. So anybody can take this chart, measure his camera capacity. Good to foolproof the machine learning algorithms. And here is the translation of this vision chart capacity. This is for 2 megapixel, this is for 8 megapixel, and the blue line represents the confidence of detection of human target at different distances. So you can see how much stopping distance or shooting distance you can gain based on the sensor resolution. And the dotted line shows the cost of detection, how many transistors are needed based on the object dimension in pixels. So in our lab, we are doing optimization of demosaicising, sharpening, noise reduction, and tone mapping to increase the detail reproduction. And we can increase these metrics by roughly 10-15% by proper tuning, sometimes 20. And for dynamic range, I'm using here an image test contrast resolution chart, and the lower diagram is how we evaluate the dynamic range capacity. The maximum brightest chart minus the sorry, I had a slip of a tongue. So the brightest patch and the darkest patch, which we can capture within a range of SNR below a certain level, which we describe in the test. So this is good for L2 kind of measurement, and for L4, where we want to see capacity of detection through the whole dynamic range, we also observe the information or contrast versus the SNR at each patch by observing the volume of this black body in the middle. And for lens flare, I currently don't have a setup. I use simple LED lights and flares, and I control the lens flare by tuning, by adjusting gamma and sharpening and other functions. And for advanced apple-to-apple comparison, it's better to use the environment provided by DxO and ImaTest. They're slightly different by the standard, but for scientific purposes, one is better, the other is better for industrial use. So for dynamic range and HDR optimization, I control exposure operational range, ratios between exposure, and tone mapping parameters, tone mapping algorithms like Iridix and NVIDIA curves. So we adjust the asymmetry LUT to expose highlights or shadows better. And the last metric is color reproduction. For traffic light model, it's very important. And when we are doing proper color, talking about proper color reproduction, we are observing patches 16 and 15. So 16 and 15, I'm showing with my mouse here. So we're observing their captured values and reference values. And we're trying to minimize the norm of differences of between differences of two projected and perceived values. So basically what we want to do is to achieve that when we applied our color transformation, our distance between two targets is not increased compared to the before color correction. And we want to base our color processing So it equally quantizes the error between the two colors. So probably we'll need a separate presentation on that topic. So yeah, thank you very much for giving me a chance to present. And I'm reachable at timo@fourierimagelab.com.